All right, so now we're gonna go ahead with the rest of the homework questions. And here we have number 4. First, draw it out. We have a 10 centimeter long rod, so let's draw it. And there you go. And it's 10 centimeters long, so here we'll, this is my L. I'll write it here to the side. L equals 0.1 meters. All right, and we have it is charged, so this Q1 for this rod is equals to 10 times 10 to the negative 9, and 10 centimeter long plastic rod uniformly charged. So we have another plastic rod right here that is also uniformly charged. No, these are some shitty looking lines, but it works. All right, and so this length is also 0.1, but my Q2, so we'll name this Q2 and we'll name this Q1. All right, my Q2 on the other hand is a negative, so it is 10 times 10 to the negative 9, so it is the same charge. However, this one is negative, right, and this one positive, so on. All right, now what is the difference between the two? Well, not difference, but what are they asking for? What is the, so they're saying they're 4 centimeters apart, so there's some distance apart. Some distance apart, and I'll put my distance up here. As you can see on my diagram, I never put numbers, so it looks clean. And I put all my details on the side so I can find them in the same spot. And apart, what are the electric field strength E1 to E3 at distances? So this is going to be my E1, E2, and this is my E3 at all these three distances from the glass rod along the line connecting the midpoint of the two rods. So they're telling us go to the midpoint of, so some L divided by 2, some midpoint, right? I'm assuming this is the midpoint. And they're telling us that I'm going to do the 2 centimeters since it's halfway, right? This is 4, and so it's halfway. And so we're going to go here at, what should I name this? X, at X, and here we're going to say X equals, so if I take this out of the way, 0.04, just to stay consistent with meters, and this is 0.02 meters. Okay, now that I'm trying to do this, we just did it earlier, and we said, we take small section, we do our E, but first we want to do the logic part. So the logic part, obviously we're going to take some small section here, and the logic part is that this will exert some force this way, and this will exert, if I'm taking a piece from here, this will actually exert more force this way, right? So whatever the force, it's times 2. Okay, so here we're going to say whatever the force, it's times 2. Okay, so just x2. Okay, now we're not done with this statement yet. We're going to do some more checks to make sure this is valid. Now, when this pulls it, so, oops. Now, let's remove this. When this rod pushes the electric field this way here, right, it has an X and it has a Y. Now, when this pushes on it that way, it also has an X and it has a Y. The X's all go in this direction, as we can see, but the Y's, one goes up, one goes down, so it cancels out. So the Y actually doesn't matter. Only the X's matter, right? And so that's my first statement, is that only EX matters. But we only check that for my red rod. Now let me check for the blue rod, and we know this pulls this way, and this side pulls that way. Obviously the middle pulls here, which has no Y component anyways. But here, when this pulls, it also has an x this way and a y that way. And this one also has an x this way and a y this way. So we notice, oh, well, that's actually the same thing here. Y's don't matter. And so, okay, so this is for the red rod and the blue rod. So when I say only EX matters, that is valid. That will calculate my EX in this direction. And then I'm only saying whatever the force is, it's times 2, because obviously this exerts the same force. And this is only true because the charge is the same for both of them. If the charge was different, then it would be different. And if the length was different, it would also be different. And so remember, I'm just doing this to save time using some logic. All right, now that we determined this, let's do dq quick. Oops, dq over dy, right? And I'm going to name this ground 0. This is going to be my L over 2. This is going to be negative L over 2. And as you do practice, you'll understand it so well that you don't need to memorize it. You just know, like, you know what, I need to do this. Okay, so my EX, I know it's E cos theta, right? Because I'm using this angle right here, which is this angle right here. And when I'm looking at it this way, this is my EX. And so this is my E. Rearrange this, you'll get this this equation. EX equals E cos theta. Now I know, obviously, my E, which is K dq, because this equation right now I'm calculating, so this is DEX. I'm going to name this DEX, right? This is also DE. This is also my DE. Okay, now what I'm calculating here for my DE and DEX is for this little piece, right? So therefore my DQ is also for the little piece. And so DQ over my R squared cos theta equals DEX. Now equals, now we have too many unknowns. We want to put them all in the same term. And so I'm going to need first my DQ in the terms of y, right? And so I know this little piece has some length dy. And so lambda equals the charge, which is dq, over the length, which is dy. So now rearranging this in terms of y, this is what I get. So lambda dy all over my r, I also want in terms of y. So I can use Pythag, and that would be d squared. Well, in my case, actually, I have an x here now for this distance. So all I'll say is x squared plus y squared. Right? And now take this equation, put it here. But obviously, I have a square root. I have a squared, and square root cancels out. All right. Now I have cos, and I want to turn this also in terms of y. And so obviously, this is my r. And so, well, cos is adjacent over hypotenuse, and my adjacent is x, and my hypotenuse is r. And so I'm going to be like, well, in that case, I'll just replace it. And so there you go. X, r, and then r is squared. And so x squared plus y. And now that's all. My x is given, by the way. It's 2, right? It's up here, 2. Now my y is not, though. So this is everything in terms of y. So times x over x squared plus y squared rooted. Now remember, we explained this, how I got this. If you want, watch last lecture and the last part. That's where you'll find this exact lecture for this whole actually problem. And so, like in details. And so this is x over, this will be x squared plus y squared equals 3 over 2. Now what I want to do is integrate and add all the little pieces together, right? And so all I get is EX equals K, constant, lambda, constant. My lambda, when you're going to look at this, you're like, wait, how do I get my lambda? I don't know dq, I don't know dy. Lambda is the same everywhere. So your lambda of your q1 divided by L is the same. But remember, your lambda for your blue bar is technically supposed to be different because it's a different bar, but the charge and the length is the same. So the lambda is actually the same for both. Okay? But this lambda, the lambda of this whole rod is the same as the lambda of this little rod, because that's just density. Density is the same everywhere. So you can calculate your lambda using this equation, which is Q1 is given and your L is given. Okay, now take this equation, sub it in for lambda. You don't have to, I'm not going to sub it in. You can just calculate it, sub the number in if you want. My x is also given, so that's constant. Take it out. Now I have the integral. I'm taking the integral from negative L over 2 to L over 2. All right, and now what I have is dy over x squared plus y squared 3 over 2, right? And if I redo this, sorry, not reduce, like integrate, I meant. What I'll get is y over x squared plus y squared. This is actually square rooted. This is given, by the way. You don't have to know how to integrate this. All right. And obviously I'm taking it from negative L over 2 to L over 2. And you can sub this stuff in and get your equation and sub your numbers in. Don't forget that this equation will give you the electric field that this rod is causing, which is in this direction. But obviously this rod also pulls in the same direction and has the same charge, same length. And so whatever you get here, it's times 2, and that would be your E. All right. Now, your answer that you'll be checking for is this one, because we're doing the 2. But if you want to do your 1 and 3, all you got to do is change your x value from 0.02 to all that. Also, another thing is, remember, when you plug your x and y's here, you got to turn them into meters before you plug them in. Because if you plug in centimeters squared plus centimeters squared, this will not give you just centimeters. It's kind of a little bit weird when it comes to square root and squaring and units. And so you can't really convert this just to meters right away. It's not the same. And so plug them in as meters to make your life a hell of a lot easier. All right. And so that's the problem for this part. All right. So now this question is a very common question. And there's actually 3 of them in this sheet. So I'm only going to do it once. I'm going to leave the rest to you. This is one of them. I believe there was a very similar one up here somewhere. This is the second one, which is what I'm about to do. And I believe actually these are the only 2. Maybe I was wrong. But this is a very common question. So here it says, what are the strength and direction of the electric field at the position indicated? So this is the position we're looking for. And give your answer in component form. So they want it in component form as a magnitude and angle measured clockwise or counterclockwise from the positive x. So they want basically degrees and component form. So let's do it. Obviously, like we said, when you're looking at electric field, split it into components. Easiest thing to do. Like different components. And so here we have our first component, which goes this way. Right. I think when I write like bigger, it is a little bit nicer for some reason. I'll make it big. All right. So the electric field is this way here. And so this is my E. And I'm going to number these to make my life easier. So this is Q1. I'll write it better. Q1. This is going to be Q2. And this is Q3. So what is my Q1? E equals K Q1 all over R squared. Now the distance between them is 3 centimeters. And we're going to convert that into meters. And so I have K times my Q1 is 10 times 10 to the negative 9 all over. And I made a little mistake here if you notice it. 0.03. Now when I calculate this, give me 1 second. All right, so what I got here is 9.98 times 10 to 1, 2, 3, 4 times 10 to the 4 newtons per coulombs. And we're going to say, I like to put like a little arrow to indicate this electric field goes downwards. And the thing is, also I'll put here Q1 to know that this is for my Q1. The mistake I made is since this is negative, this E is actually going towards. So if you notice that, you're on top of your shit. So this is my E Q1, goes towards. And this right here is the same thing. So it goes towards, and this is my E, Q3. And if I calculate it, Q3 is E equals K Q3 over R squared, which equals 8.99 times 10 to the 9 times my charge, which is 5 times 10 to the negative 9 all over. Remember how we said do meters, because this your K is in meters, so you have to have all in meters, and so this is 0.05 squared. All right, and there's a squared here as well. And so getting this is, what I get is 17,980, which is equivalent to 1.79 times 10 to 1, 2, 3, 4 newtons per coulombs. This is my Q3. And now I need my last Q, which is Q2. Q2 is a little bit trickier. It's not that hard, but remember, your equation my R here is actually the distance between the charge point at the point charge and what I'm measuring at. So the point charge and this is my R. Don't forget that. And so what this is Pythag. So here R equals the square root of 0.05 squared. Remember, convert it in meters, plus 0.03 squared. And this will equal, let me see. So that gives me 0.0583 meters. And so I'm going to take that, plug it here. My K is 8.99 times 10 to the 9. All times my charge, which is 10. And remember, this goes away. Right? This is Q2. All right, times 10 to the negative 9. All over my R, which is 0.0583 squared. And that will get me 26449, which is equivalent to 2.64 times 10 to the 4, I assume, 1, 2, 3, 4 newtons per coulombs. All right, now that I have all the information I need, I gotta, well, combine them. Now, the only problem here is these two, this is in Y format, and this is in an X format, okay? But this one is at some angle. And so what I need to do is combine all of them and see what it goes. So now first I'll take my EQ, which is my Q2 right here, and I'll split it into my X and Y components. So I know that it goes somewhere in this direction. Oh my God, I can't draw for some reason. For some unknown reason. But here, let me try again. So this is here. Right? And that is my E. And then so I have some angle theta here. Now, what is this angle? How can I find it? Let's see. Since this angle goes this way, this angle is the same as this angle. Now, what is this angle? It is the tan inverse of these two. Right? And so I think this is like a flipped angle, which I'm finding like a little bit weird to look at. But this is what it looks like. This is the angle we're looking at. This is 5. This is 3. And so if I want it, and this is obviously my R, which I mean I don't need. So this angle equals opposite over adjacent, which equals theta equals 10. All right. And so this will give us 59.03. And so you see now that gives us the angle right up here. And so I can get my EX and Y. And so my y, my e in the y equals my e times sine theta, and my ex equals e times sine times cos theta. And these will equal the following. All right, and now we got our 2, which is 2.27 times 10 to the 4, and 1.36 times 10 to the 4. Now we got all our components. So if I take this point charge and I try to explain it, so if I make it blue, right? And if I'm trying to explain it, what I have is I have one force in the x this way, and that is my EX2, right? Q2. And I also have a force downwards, and this is EY2. And then I also have a force upwards, and this is my E2. Well, this actually, sorry, 1. Q1. And then I also have a force this way. That is E3. And so what you have to do is just combine all these together. So let's do that. We have E1, which is, so if I'm doing my EY total, I'll have E1 plus EY2, which equals, we have 9.98 times 10 to the 4. Obviously, I'm just going to use the regular x-axis, so up is positive, right is positive. And so that's my y, up is positive, the bottom is negative, so it's minus. And we're going to have EY2, which is 2.27 times 10 to the 4. And so that's 1. And then EX, whatever that equals. EX of the total thing is going to be E3 positive minus EX in the 2. And my E3 is 1.79 times 10 to the 4 minus 1.36 times 10 to the 4, right? And that would equal the following. And these are my answers. And since we said we're using the same regular axes, if it's positive, that means it's going up, right? If it's positive, that means it's going up. And here my EY is 77.71 times 10 to the 4. And my X goes positive as well. And so we'll just use it this way. Connect tail, head to tail. And this is 4.3123 times 10 to the 3. That way. And so that's my EX. And that is my EY. And so now obviously they actually want it in exponent form, so I don't even need to sum the E up, but I need to know the direction, right? And so they want the direction from the x-axis. So I'm gonna have to write this format in the x-axis format. And so my x first and then my y later. And this is the angle I'm looking for, right? This is the same thing, basically. I just rewrote it a little bit differently, right? And so taking all this away, how do I find my theta? Since I have my y, which is 7,100, and I have my x, which is 43, then I can just do tan inverse of 77,100 over 4,300 equals my theta, which equals, let me see, which is 86.8. All right, and that is obviously counterclockwise from the positive x. And so now if I were to rewrite this, my E equals, obviously my E to the x, which is 4.3 times 10 to the 3. This is going to be I hat, that's J, Jesus, I hat, because it's positive. Now my y is also positive, so plus my y, which is 7.7 times 10 to the 4, j hat. And then I'm also going to say 80 counterclockwise from, counterclockwise from positive x, 86.8 degrees. Now to confirm our answer, what do we get here? 4.7 times 10 to the 3 and 8.6. So there must be 8.6. There must be some, which calculation do we do here? There must be some mistake I made here. Give me 1 second. Okay, so the mistake I actually made is right here. And this angle theta that I was looking for is actually this angle correspondence. And what that changes is that my tan inverse, which I did right here, is not 5/3, it's 3/5. It's 3/5, which changes it to 30 degrees. 30.96. And so this angle becomes 30.96. And that means these calculations will change. So let me change these calculations real quick. Okay, so I just changed all my values and all my values that relate to this mistake that I made here. And so now I got 8.62 and negative 4.8. And after that, now I have my E and X, obviously in total. And so my E in the X and E in the Y, my Y still goes up, but funny enough, my X actually goes across the other way, which is this way. Right? And so my angle now is here. But remember how I said I want it in the X? So I can still get this angle, and this will technically still be in the X. And so, but technically that wouldn't be right. And so if I want to actually put it in the X, I'll have to put my X. So this is my X, let's say. And obviously my arrow goes this way. And it goes that way. And it goes up. And so we can say this is the angle we want. And so that's something, but they want it from the positive. So they want it like in this direction. So there's a way you can kind of flip it, which is you can say, you know, whatever this angle you get, or you can say whatever this angle you get plus 90. So all these way work. So I'm going to use actually this one plus 90. And so this is my theta. And obviously my X is 4.8 times 10 to the 3. And my Y is 8.62 times 10 to the 4. And so my tan inverse of opposite over adjacent, which is 4.8 all over 8.62 equals my theta, which equals, let me do that. And so what this gave me is 3.18. And obviously they want it from the positive X. And so what this will be is 90 plus. 90 plus whatever this angle is, which is 93.18. And so my answer is, in component format, E equals whatever my X is. So my X is negative 4.8 because it's going in the negative direction, right? It's going this way. And so it's 4.8 times 10 to the 3 I hat plus my Y is going up, so it's positive. That's why it's a plus 8.62 times 10 to the 4 in the J hat. Okay. Now, if they want us to combine this, you'll use Pythag to get this E, right? And then your angle will be 93.18 counterclockwise, lol. Counterclockwise 93.18 clockwise from positive X, which is what they wanted. All right, and so that's how you answer that question. Hello, everyone. How y'all doing? Currently it's 1 a.m., actually 2 a.m. And this question have puzzled me for some reason because the axes changed, right? Before, we were actually working with examples that were more vertical and there was some point charge. And there was usually some symmetry. However, in this question, that all goes out the window. And I got really puzzled. But just now, I was in bed and I was just thinking about this equation. I was like, how do I solve this? And so it hit. And so I got out of bed and now I'm here teaching it. I haven't tried it yet, but I'm pretty sure it works. All right. So this question, what it states is, find an expression for the electric field strength at point P on the axes of the rod at distance r from the center. And so, in order for me we get the charge that this experiences, this point. And the funny thing, nowhere on the internet does anyone explain how the axes are actually set up. All right, and that's what I figured out halfway asleep. And so basically, if I want the charge that this exerts on this, is obviously this way, right? And now I don't have any electric force upwards or downwards. There's only electric force that way, right? But the electric force is different. Now, if I go here, the electric force this block exerts here is some power, let's say E1. Yet, the electric force that this block exerts on here is a smaller E2, right? And so the electric field changes depending on where I am on this rod. And so, well, how do I calculate this? The thought is choosing the x-axis somewhere, then it makes it easier for 2 points. Point 1 is that it cuts the problem in half. Point 2 is that you get to decide how far you are in your R terms. How far you are from the problem, something that's easier to say. So what I'm going to say is I'm going to say x equals 0 at this origin, which is the half point. That's where it's going to be my x equals 0. Now this is going to be my x, and this is going to be my negative x. All right. In other terms, this side is my negative L over 2, because this is all of L. So if I divide L over 2, this is the half of L. And this is the positive side of L. In other terms, L over 2, positive. All right. Now that I have this, what is the electric field here? Well, I can't really calculate the charge on all this, but what I can do is separate it into one small section. Okay. Now this section I'm going to call charge dq over dx. All right. Now, what does dx mean? It means the change from x here all the way up to some x here. And the area in between this is my dx. And that gives me actually the length of this piece. Dx is the length of this piece. All right. So what I'm going to say is, well, since lambda equals q of the whole rod divided by the length of the whole rod gives me the density of the charge on that rod, then I could say, well, the charge of dq over dx is the same lambda, right? Because this lambda is constant no matter if I take small box or big box, right? It's just density. And so since this equals lambda, what I can say is, well, before I rearrange this, let's go to the electric field equation. My electric field equation says A Q over R squared. R being the distance I go from my point charge all the way to my charge. So that is my R. But here my R is denoted as the distance from the point charge to the center. So we're going to actually denote this as D. All right. R is this distance. Okay. So we're going to get rid of this. Now, K is a constant. My charge of the small piece is dq. And my R distance, well, how far am I from the point P? Now, I know as I move along the x, let's say first I get this little piece. This little piece is some x distant away, right? And so if I take my R, which is, so let me clarify this section. And we said this is going to be my D, right? Now, if I take my D and I say, well, I shall use the same example I drew. So what I say is, well, this section here, I go from x0 all the way to x, right? And so that's some distance x here. So what I can say is my R, this R, is D minus x. So D minus x will give me my R. And so what I could denote this as is d minus x all squared. D minus x is my r, and I just simply square it. Now the question is, well, d is a constant, then, well, what is my dq? Obviously, lambda dq over dx works. But here, this x is an unknown. And so, well, what I can do is change dq in terms of x, so I can integrate. So lambda equals dq over dx. All right, and lambda dx equals dq. And so bringing that in here, lambda dx, and now bringing that in here, what I'll get is k lambda dx all over d minus x squared. Now what this little piece generates is it generates some small dE, right? This small point of charge makes a small dE. And so what this is it's dE, right? Small point creates small electric field. Now, if I take this and I integrate both sides, I will get electric field equals to, well, k is a constant, lambda is a constant, dx is not constant, so this is the square root of dx all over d minus x squared. Now, what am I taking this integral from? I'm taking it from L over 2 to negative L over 2, or the other way around. So negative L over 2 to L over 2. Now that I've explained this here, what I'll do is integrate. An integral is always given, so I'm just gonna search it up. And here, my integral goes 1 over d minus x square rooted. So let's get my final integral here. Is that the integral? Actually looks pretty simple. I'm surprised. Let me double check. 1 over, so I'm gonna move it to the side. And what I got is k lambda. And I got 1 over d minus x squared. Well, not squared actually. I got d minus x from negative L over 2 to L over 2. Right? Now substituting this in, what I'll be getting is k lambda square 1 over L over 2. Well, d is a constant. L over 2 minus 1 over negative L over 2 minus, well, oops, again, mistake, d plus L over 2. Now, if I take this and I simplify it, what I'll get is k. Let's get a common denominator here. I can just minus the 2. So I multiply this by the top, multiply by the bottom, multiply this by the top, multiply by the bottom. So what I'll get is lambda, and I'll get d plus L over 2, right, to times the top and then times the bottom. So what I'll get here is d minus L over 2 times d plus L over 2. Right? All this minus, multiply this by the top as well, which is d minus L over 2. All right? And so, doing this, let me see what I messed up here. This gets multiplied at the top. And I believe it's supposed to be like this. All right. Now, just expanding out everything. And so this d, let's expand this out. It'll be a negative d plus. So it'll be a lambda negative d. Well, first I have a positive d plus L over 2 minus d plus L over 2 all over d. So if I expand this out, what I'll get is d times d squared plus dl over 2, right? And then times the negative in there as well. This will be also negative dl over 2. And what I'll get is also negative L over times this, which is minus L squared over, well, yeah, L squared over 4, right? Now this and this will cancel out. So what I'll end up with is K lambda. And this will cancel out. So I'll get L over 2 plus L over 2 all over d squared minus L squared over 4. Now after I have this and I add them together, what I will get is, K lambda, and this becomes 2 L over 2, right? And then so this cancels out, I just get L divided by d squared minus L squared over 4. And so now these two obviously cancel out. And so what I'll get is L over d squared minus L squared over 4. And this equals K. My lambda is actually Q over L. So expanding this in, I'll get K, Q, all over, or if I want to write it in their terms, 1 over 4 theta epsilon naught times Q, L, or over L times, and this L comes from Q over L, times d squared minus L squared over 4. Right? Now these two L's will cancel out, leaving us with a nice 1 over 4 pi epsilon naught times Q over d squared minus L squared over 4. And what is the answer for this equation? 1 over 4 pi epsilon naught. Oh, it's right here. 1 over 4 pi epsilon naught Q x squared minus L squared divided by 4. And my x in my case is my d. And that's about it. Whew, I'm so glad, dude. I guess my dreams do be working sometimes. Alright, this is an achievement. I actually gotta send this to a prof because I was talking to the prof over email, and I was talking to him about this specific example. So I gotta show him that I got it. I'm so happy. Okay, so now next question 8. Alright, so for this question is a very similar concept, just a little bit different. And the difference here is that obviously this is a half circle, semicircle. And so what I first like to do always is just select a couple pieces from random spots and see how they act on the point charge. And the center where I'm trying to measure my electric field is right here. And so this will push it down, but the bottom piece will push it up. This piece will push it at this angle, and this piece will push it at that angle. Now, this piece will go straight up like this, and this piece will go straight down like this. And so you see that my y-axes all cancel out. And that tells me that I actually don't need to account for my y and only my x. And so now that I know that I only need to account for my x, which is going to go straight to the right. And that would be my EX. Now that I've gotten that going, first let me select a random piece that this is what I'm going to be calculating for, because remember, we want to split it into very small pieces and then calculate according to that piece and then integrate over the whole thing. And so now that I have this, let me get the density of the rod. And so the density is the whole charge of the rod over the whole length of the rod. Now, since I'm only accounting for this piece, now what is this piece's charge? I could say that this piece's charge is dq, a small piece of charge. And well, what's the length of this charge is also a small length. But what is that length measured in? Now, obviously, this is a semicircle, therefore this is a circumference. So I'm going to denote circumference as S. And so now, if I'm taking this and I'm turning it into relating it to the small piece, what I'll say is, well, then my lambda equals my little charge dq over my little length, which is ds. All right. Now that I have that going as well, let me draw the electric field that this will actually cause, and it will cause an electric field that goes this way. Right. Now, obviously, like we said, we want only our EX. So let's write our equation, which is E equals K Q over R squared. And since I want my EX, it equals to my E cos theta. And this theta would be the one right here. Now, in order for me to get that theta, well, first, what is my R? I know my R is some distance away. Well, this actually should be like, the piece should be perpendicular, like here. Actually, I'm gonna move the piece there so that the drawing looks nicer. So we're accounting for this piece, which has dq and ds. Okay, and ds is for how long this rod is. This little piece of rod. And so now I know this is my R, right, which is my radius, as well as the distance between the point to the charge. So now when I rewrite this, what I'll get is K, my Q, I'm getting this one charge, which is dq, over my R, well, that's the radius, so we'll denote that as capital R, or radius squared, right? And obviously I still have my cos theta. And here now what I have is dEx. It's also a small piece of electric field. And so so now I gotta find my theta. And I know this theta is the same as this theta, right? And we know in other courses that the circumference, sorry, on the side with the pungent with the equations, the circumference is equals to my R, which is the radius, times my theta, right? But since we're accounting for only a small piece of ds, then I can turn this into ds over R d theta, a small amount of d theta as well. The radius is constant, stays the same. So now that we also accounted for our theta here, okay, well, what's my dq? My dq is the same thing as if I said lambda ds equals dq. I'm going to take that, let's sub it in. So all I get is dEx equals K. That would be lambda ds all over big R squared cos theta. Now, I have obviously a theta and I have a ds, so I can't really integrate this. But first, let's write out our integral. And so what I'll have is the integral of dEx, and the integral, well, k is a constant, comes out, lambda is a constant, comes out, my radius is a constant, comes out. Remember, for my vertical rod, when I had a point charge here, my R was changing. The R up there is different from the R down here. And so my R would change as I'm doing it. But for here, the radius is always the same. And the distance from the center is always the same. So R is a constant. So all I will get left is the integral of cos theta ds. Now obviously I can't integrate this because these are in two different terms. So what I'll get is Ex equals K lambda over R squared. This is just constants. Now what is my integral? Well, my cos theta is in terms of theta. Can I change theta in terms of S? I mean, yeah. I can divide this by R, and, well, that's not theta, it's d theta. But, well, I can change ds, though. I know my ds equals r d theta. So, well, I can do that. So cos theta equals r, well, not equals, but my ds becomes now r d theta. Now, like we said, r is a constant, so actually I could take this out here. And so what I'll get is ex equals k lambda r all over r squared. Obviously, this will cancel out. And you see now my integral simplified a hell of a lot. And so my ex equals now k lambda over r. This my r is one of them cancel out. And my integral will become sine theta from some bounds. Now the question is, what are these bounds? One way I could do it is I could go from 0 to pi over 2, right? So if this was a graph and this was a semicircle, this would be 90 degrees, pi over 2. And so that's one way. Or, and then times this by 2, because obviously I have this section. Or I can go all the way from negative pi over 2 to pi over 2. And so that's probably the easier way to do it. And so this will be my bounds. And so now I will go from negative pi over 2 all the way to pi over 2. And so writing this out, what I'll get is k lambda over r sine pi over 2 minus sine negative pi over 2. And pi over 2 will give me 1 minus, this will be negative 1, so this is 1 plus 1. And so what I'll get here is 2 k lambda over r. And so far so good. My lambda is q over l, so let's replace that in. And so what I'll get is 2k q over l r. Now obviously I have l and r. Why do I have l and r? I know for a semicircle, obviously we wrote it up top, s equals my r times theta, right? And well, s is the same thing as l, right? So because the circumference is this, and that's l, and so I could actually rewrite this as l equals r theta. Now, what's my theta? What is my circumference of my theta? And I know my circumference, which is l, equals to the radius times my theta, and my theta is, well, that's half a circle. Theta for half a circle is pi. And so that'll be pi. And so now what I could do is rearrange this to solve for r. And so what I'll get is l over pi equals r. And so, well, okay, then I can take this and replace it here. So I'll get is 2k q all over l over pi times l. So that's the same thing. If I flip and multiply, I'll get 2 pi aq all over l squared. And what was their answer? 2 pi q over l squared. And we have k on the outside. And so if I rewrite this in their terms, this would be 1 over 4 pi epsilon naught. And I'll have 2 pi q all over l squared in the pi direction, which is my x. And that is how you solve this equation. A little bit lengthy, but not too bad.